Okay, so today we look at Jacobian control of the 3D manipulator. Okay, so the planar was simple and to introduce you to the concept. So, so first let us look at the class of problems we are looking at. So, suppose we have the task of welding along this edge followed by this edge. Okay. Now, you know this much from welding that you should attempt to make sure that the welding rod as it traverses this is equally inclined to both sides. So, similarly here it is equally inclined to both sides. However, you will have to do a transition in the middle because you are going along this inclination and then you are ending up with this inclination. Somewhere in the middle you have to transit between them. The other thing is that while you are welding, you want to maintain a constant bead rate. Okay. So, it is convenient to specify velocities that okay, you just move along this with a certain velocity which you define. And so, to maintain the orientation, you just specify that you please do not have zero angular velocity as you are traversing it. So, then you just maintain the constant bead rate. So, this class of problems is very conveniently done through Jacobian control, okay, because you are specifying the rates of traverses. So, when you are specifying the rate of traverse, that can be mapped directly into angular velocity of the joint motors. Okay, so, that is convenient. So, now this gives me the opportunity to talk about this thing about velocity driven systems. Okay. So, when you do control, there is a lot of focus in getting to a position and stopping there, PID feedback, but through PID you have two options. You can either control position or you can control velocity. Okay. So, we look at these two cases separately, and if you look at a proper commercial controller, like you have gone and seen the KUKA, right, that has two modes. You can either work it in position control mode, so it will go from one position, stop at the next position, then go from one position, stop at the next position, or you can run it in the velocity control mode where you can specify velocities. Now, so let us look at what the situation is. So, suppose I want to move steadily, so my displacement S is increasing over time. Okay, so, this is the desired output I want from the robot. So, I could move in a straight line, I could move in a curved line, but some desired along the path I am moving it with constant velocity. So, you can split the path up, you can calculate positions, and then you can do inverse kinematics, and then you can say okay, you go from this position to that position, this position to that position. Through inverse kinematics you can break it up and you can reduce it to joint motions which are executed. Now, what would happen is you would start, you would gain some velocity, then you retard and you come down to zero velocity. Then you get the next target, you start, you retard. Now, this may not be a straight line, this can be obviously, you will not start with finite velocity after you have stopped. There will be a small curvature here because there has got to be finite acceleration, there has got to be finite jerk. So, all of that is going to modify this curve. Instead of being a straight line, it will be some polynomial or whatever, a little variation, but basically it will move around this, that you are going to start and you are going to stop. On the other hand, if you are going through the velocity control route, then you could essentially run with a constant velocity, which is what is suggested here. Okay. Now, you are not going to run with constant velocity because you are going to have a profile which is rounded here and a profile which is rounded here when you stop. So, you will have a little variation around the red line path, okay, but generally that will be the path. Similarly for this, generally this will be the path with small variations around this. So if you are running on a velocity control mode, then except for the two small corners around here, when you are going to slow down and you are going to more or less get a straight line. If you are doing position control, you know that this is a ramp, so the displacement will be a what? It will be a quadratic, right? So it will not be a straight line, you will get a variation like this. You will start and then you will cross over here, you are going to land up here with 0 velocity. So it's going to approach this from tangentially along the 0 line, it is going to start tangentially along the 0 line, it is going to go up, exceed this and then come here, and then it will again go like this, it will come up. So it will wriggle around the black line. Now this start stop thing is not nice. So it will create all kinds of essentially that leads to higher order dynamics, and then you have noise. Keep. So it will keep on making these kind of noises if you are programming it like that. Okay. So this higher order continuity in the velocity control mode is very desirable for many situations. Okay. And that comes almost directly from the Jacobian control approach. So now when I say most robot controllers are equipped with velocity and position control, they are somewhere down the line implementing this stuff that I am talking about, number one. Number two is, so when you saw the KUKA, you would have seen that for each axis there is a box which is there. Okay. So that is the motor driver. And then there is a controller box which is there, which has all the kinematics equation for the robot. Then when you give a command to each of these joint, okay, that is interpreted and that box controls that joint. Now that individual joint with a proper controller can be controlled to either go from say theta is equal to 30 degrees to 60 degrees. So start from there, it will accelerate, reach a velocity and then come down. When you reach 60 degrees, it will start slowing down, and so that it settles down there. The other option is you can just ask that joint to move in a velocity control mode. If you look at an NC machine, typical NC machine like an NC lathe, so the spindle you will control typically in a velocity control mode. You specify the spindle speed. On the other hand, the feed and other things usually you will move in position control mode. So go from one position to other and then you do a cut and then you change again. So you have both of them, and most industrial manipulators, they have actuators, the drivers which can work in both modes. So you could switch them, you can switch it programmatically. And this is the reason why it is implemented, that it is not very good to basically go from point to point, stop, start again, stop, when you know that you want to move continuously. Okay. So we now come to the problem of transiting the edges of the box. So I have specifically shown the transition as black lines. So I am moving from the red lines and going to the red lines where it moves steadily. So in between I have to transit, so this line is close to this line is close to this, so this is a little variation, this is a little variation, this is a little variation. Okay. So if I am welding around here, so I start from this edge, fine, I keep coming, but somewhere here, I know that when I am here I have got to be looking like this. So I have got to do this transition, so from this to this. Okay. So that is the transition I am looking at. Now when I want to do this transition, I still want to maintain the bead rate. Okay. So I can keep going with specify a tip velocity to continue here, and then once it comes here I can say, okay, now you change the tip velocity to this, so that my bead rate is maintained. Now in this I am going to, so the simplest way of programming it is to say, okay, you come till here with this orientation and then you change the orientation. But if you do that, then while you are changing the orientation, your tip will be sitting here. So you are going to do a burnout here and the beading is going to be different. So the better option is to, as you are coming along here, you slowly start transiting so that when you've come here, you're okay. So that will be the idea. Okay. But we already know how to do something like this very neatly. What we do is we just find out that going from here to here, what is the rotation axis? Right, we did it about a month ago now. Okay, we can find that out. So you find out capital omega t, the transition axis. You find out the rotation amount theta. You divide it by the time I am giving for the transition. Okay. So then, in the Jacobian control, you can just specify the angular rate as, so you divide this theta by the time interval delta t, so that gives you a velocity like term and this gives you the axis. I mean, I am just taken capital omega t and take the x component, y component, z component. So that directly gives me the omega I must program for the Jacobian control. Okay. So this is the essential reason why we need Jacobian control in 3D more than anything else. Well, we also need it in 2D for similar reason, but I didn't want to discuss it. I mean, these kind of details there. So are you getting the essence of it now as to why you need it? I want to do velocity control. And there are other advantages of inverse kinematics, as we will see. Now, when we did the planar Jacobian, we looked at a term like this, right, where we had in 2D we had position and then we had only one angle which characterized the Jacobian. So we looked at the rates and we related it to theta 1 dot, theta 2 dot, theta 3 dot, and it was very simple to find out the rate of motion of the end effector. It would simply be the sum of the rates of individual relative joints. So it is 1 times theta 1 dot plus 1 times theta 2 dot plus 1 times theta 3 dot. Okay. And we obviously know that if you multiply the joint rates by the Jacobian, then you get the Cartesian rates. Okay. Now, when you have a 3D manipulator, the joint rates are very similar. You just have a single motor at each axis, right. So again you have theta 1 dot, theta 2 dot, theta 3 dot, 4, 5, 6 dot sitting there. That is not changed. You still have motors, right. There is no other funny actuator which is around. Though you can combine them, you can have a wrist actuator which is actually 3 degrees of freedom. So that we will see when we do parallel manipulators later. They can be funny one, but fundamentally your actuator is a single degree of freedom actuator. In the plane, we have two coordinates px and py. Okay. In 3D, very simple extension, you have pz also, right. And then, so you had px dot, py dot, if you take pz dot, so that gives you the velocity vector. So this extension is extremely simple, no problems. Now rotation in 3D we know is always a little bit of a pull-push kind of situation. And so in the plane, this single parameter capital omega, capital theta was fine because all the rotations were perpendicular to the plane of the motion. And you obtain theta by summing successive rotations about each axis. In 3D we have a problem because we need at least 3 parameters, it's 3 Euler angles, or you need the 3 by 3 rotation matrix, which we said again has essentially 3 independent parameters, and there are other notations also. There are 3 kinds of Euler angles, there is quaternions and there is screws, so all kinds of options. But whatever you do, it's a 3 parameter system, not a single parameter system. And not only that, they are non-commutative, they don't add. This is something which you have known for at least couple of years now. However, you also know that infinitesimal rotations, and they are vectors and they are commutative. You can add them vectorially, they have don't have this problem that finite rotations have. And so the time derivative of infinitesimal rotations is the angular velocity vector, and which is very nice and well behaved. Okay. It fits into all our high school physics, and so we are very comfortable with it. There are no issues there. So the angular velocity of the end effector is a linear combination of the relative angular velocities of serially mounted links. Okay. So we take the angular velocities at each joint, so that's a vector. You linear combination multiplied by the angular rate and just add them together, and you get the angular velocity of the end effector. I will forewarn you that when we do dynamics, you will realize that angular acceleration does not behave like this, right. In angular acceleration there is another term, there is omega cross omega terms which comes and will poke around and mess around. So angular velocity is nicely behaved. So angular velocity is nicely behaved, angular acceleration is okay, but you have to take care of terms, but angular displacement is a very bad boy. Okay, so very badly behaved. So any time we can get out of angular displacement, it is good. So that's why Jacobian control is so nice in 3D, because it deals with the angular velocity and not the angular displacement. Okay. So now, so there are multiple ways of doing the Jacobian. Okay. So we will first start with the definition method. Okay. So what is the definition method? So you take the angular velocity and the linear velocity components, okay, end effector, and you write an equation which relates it to the joint rates. So how do you do that? It's quite simple. We know how to calculate A60, and we know that A60 looks like this. Okay. So we know P06, right. So position of the end effector in the 0th frame we know. So this is a vector which is 3 down. There is x component, y component, z component, and we can multiply. We know what individual matrix is, so we can multiply it, and I actually showed you in the class how you multiply two such matrices and you get it. So you can multiply all 6, so you can find out P06, and then you take the partial derivatives and you are done, right. Only catch is we expect 4 to the power 5 terms, right, which is not too bad, right. 16, 64, and so 252. No? Oh, will it be power of 5 or 4? Yeah, so that's not too many terms, right. That's not too many terms, but also in addition to that, I mean, so it's a basically non-trivial task, but we have something coming to our help, because when we designed the manipulator, we made sure axes are parallel, orthogonal, intersecting, so it reduces. It's not so bad. You will end up with, I think for the 6-axis Puma 560, I mean, in the younger days we did it by hand, right, and then we got on to maxima and things like that, but you can compute it. You don't have too many terms, about 25 terms or something like that. And then you can take the partial derivatives also using Mathematica or Maxima. They can take partial derivatives of simple terms. So it is still, you can see it's not a very nice situation, right, trying to do this, but it is possible to do so, right, you can do that. The angular rates I am still not talking about, right, because if you land up with this matrix, I mean, how do you find the angular rate differential? So that's a little bit more complicated, we'll come to that. So we kind of ditched this, we said we don't want to do this. Okay. So we will take a numerical approach. Now we know that if you use screw theory, that if I write down the screws 0, 1, 0, 1, 2, so on and so forth, multiply them by the respective, these are supposed to be dots, okay. So I will correct it at the end of the lecture today. So theta 0, 1 dot, theta 1, 2 dot by the angular rates, then you will get the angular velocities and the velocities of the end effector. Do we get the velocity of the end effector? We get the velocity of the end effector instantaneously coincident with the origin of the coordinate system, okay, not the velocity of the end effector that I am really interested in, okay. But we already know that if I know the velocity of a point which is there at the origin, we can find it at some other point. So that is not too big a problem. So how do we do that? Now, so we have to do two things. We have to identify the screws and we are done. And then we have to move from the point which is there at the origin to the point which is there on the end effector, okay. So two tasks which are there. So the screw consists of two parts. One is the direction of the rotation of the angular velocity, right, which is given by each axis. The z coordinate that we have is a direction of either rotation or translation. So we have that. So we can easily calculate that because we know each of these matrices. So as you do your dh thing, you can extricate the z component and you just stack it as a column here, okay. Now, so other component is moment of a unit vector about the line, about the origin, that would form the screw, plus I have to move that, whatever I get there, I have to move it to the end effector, right. So it is a two-part thing. So what you can show is, I mean this you can go back and try out, is that if you now multiply this with this term P E10, where you define this as, so position of the origin of the ith coordinate system is given by Pi0, and then this is the position of the end effector in the 0th frame. So the difference of these two is Pi, 10. So multiplying this with this term effectively gives you the velocity of the end effector due to angular rate about the first point. So this gives you the screw, so just stacking them up like this gives you the Jacobian that you are interested in. So this is computationally quite simple. You have to do dh parameters anyway, to do forward kinematics, to do inverse kinematics. So you just keep on doing that, you just take out the z axis, stack it, you can find out what Pi0 is, you know where the end effector is, you know this term, just subtract, do a vector multiplication and you are in business, okay. This is computationally much simpler to implement than the definition method, okay, and it elegantly gives you, takes care of the rotation problem, everything, okay. Why does it take care of the rotation problem? Because this gives you the direction, angular velocity direction, this multiplied by theta 1 dot will give you the angular velocity of the end effector summed over all the joints, okay. Now, so this is a fairly effective method, but it is possible to derive symbolic form of Jacobian matrices from a complete screw theory approach, a different, slightly different screw theory approach. And the idea is that if you do this through the method which I just discussed, you only can work with numbers. So you cannot identify the configurations at which it becomes singular, the Jacobian becomes singular, because you will get a set of numbers. So now if I ask you, okay, this number is fine, now when you are planning the motion, can I know when you will reach a singularity? You can't answer that question. So that is a problem. Secondly is that inverting a So once you form the Jacobian, this is 6 by 6, and you have to invert it manually every time. Inverting a 6 by 6 Jacobian is it's computationally little difficult. I mean, not difficult, it just takes time. Okay. Plus there are some nice other things which you can see in a Jacobian matrix which you cannot see if you use the numerical process. So what we will do, in fact today we will just do this much more, is we will write the Jacobian in a convenient frame, not necessarily the base frame. Okay. So for example, we will take a T3 manipulator, okay, which is, well, a fairly common manipulator. It has, so you have this trunk rotation axis, one shoulder, two shoulder, three successive axes. Then you have this one orthogonal to this, and then this one. So it's like any other normal manipulator which you see. Even the KUKA roughly falls into this kind of a category. Okay. So only thing is whether the third one is orthogonal to this or is it parallel to this. So in this case, this one happens to be parallel. So I will take this as a specific example, but you can do it for most manipulators, a similar technique. Okay. And the reason why I am not doing it for the KUKA is because, why am I not doing it for the KUKA? Yeah, you have it in mouth, right? It will come as a lab assignment. Okay, so we will see. So it can come as a lab assignment, you can do that, and then I will incorporate it into the lectures. So let us see what am I doing different. So this is the first axis. So we will pass the first screw through this, and so I have the z axis going here, z0 axis, and then the second screw goes along the second joint. But I am now putting in the y coordinate along this direction, I am not putting the z coordinate in this direction. I could have put the z coordinate also, but that is too much complication. But by putting the y coordinate, I essentially make sure that my z1 also is same as z0. Okay. And a rotation θ1 will essentially move. So original y0 was like this, because of rotation θ1, this is moved off like this, and the original x0 was here because of the rotation θ1, it is moved this direction. Okay, now you have this. If you rotate θ2, then this x1 will start dipping down. So this becomes x2. Now this rotation will dip it down even further, this becomes x3, and this rotation will dip it even further, this becomes x4. Okay, now with the vertical, this angle is θ2 plus θ3 plus θ4. Okay. Finally, this rotation θ5 will move this in the roughly in the in-plane thing, assuming things are horizontal, and then finally you have this rotation about this axis which is θ6, which just causes this to rotate around. So we notice that there is this set of axes which stays horizontal, y1, y2, y4, y3, where is y2 gone? So these stay horizontal, so that is very nice. Okay. Now what we want to do is we want to write down the screws. Okay. Now it is convenient to write down the screws about this axis y4, z4, x4. Okay, so x4 goes along this line. So we want to write all the screws about this axis. Now it is quite obvious that at least $4 will seem to be 0, 1, 0 and then 0, 0, 0, because it is along the y axis. So let us now look at this. Okay, so we can pretty much do it by inspection, except that I am now giving you the side view of the robot. Okay. So in the side view, there is a joint here, there is a joint here, there is a joint here. In fact, there are two joints here, 1 and 2. Okay. So what we said is the $4 we decided was 0, 1, 0, 0, 0, 0, because it passes through the origin and it has only a component which is along the y direction. So quite simple. If you look at $3, the third screw, that passes through this point and is coming out of the plane, right? Since it's coming out of the plane, its direction cosine will again be 0, 1, 0. Okay. In fact, $2 is also coming out of the plane, so it will again be 0, 1, 0. So only thing we have to do is we have to calculate what is the moment of a line which is coming out of the plane here. Okay. So what is the moment? The moment about the y axis will obviously be 0 because it's parallel, no moment about that axis. So it has a moment about the x axis, right? So if you pull out on this, this will be the moment arm, right? The small dotted line which you see here, that is the moment arm. And what is the magnitude of that? This angle is theta 4, this angle in here is theta 4, so this angle is theta 4, so it is g sin theta 4. Okay, that is the moment about the x axis. Now when you pull on this, the rotation is going to be in this direction, so it points along the x4 axis. Now this also has a moment about the z axis, which will be equal to, so the moment arm for that is going to be this length, which is g cos theta 4. This angle is theta 4. This angle is theta 3, the angle here. So you have g cos theta 4. Now if you are pulling up from this point, then the moment is going to be in this direction, which is opposite to the direction shown for Z4, that is why you have the minus term in there. Okay. So this is straightforward geometry. Now you can go here, so there are two terms, f times S3 4 plus g, so this one is also in the same direction coming out. Now what is the moment of this about the Z4 and the X4 axis? So for this is coming out, to find the moment you need this length from here to here, or I have basically to overlap, stop the overlap, I have shown it here. So there are two components, you have this one g sin theta 4 and f times, now this angle here will become theta 3 plus 4, right. So you have this term, two combinations. Similarly here you are getting a negative moment. Now finally we get to this term. So we are asking for components of Z1, you can show that there is minus S234 and C234. So I am asking for components of this about X4 and Z4. Okay. So this is bent from this axis by theta 3 plus theta, by theta 4 plus theta 3 plus theta 2. No, not clear? You are not looking at the figure. We are asking that this is the Z1 axis. This is the Z1 axis and the first screw passes through this, right. So we are asking what is the direction cosine of a vector going along this in this coordinate system x4, y4, z4. So we are asking what is the direction cosine of this in x4, y4, z4, right. So that is very simple, we are asking how much is this angle, how much is this line inclined to z4 and x4. How much is x1 inclined? Theta 2 plus theta 3 plus theta 4. Okay. So if this is inclined by theta 2 plus theta 3 plus theta 4, then this is inclined by that plus 90 degrees, right? So if you just figure it in, then you will get minus sine 234 and cos 234. Just go back, draw the, sketch it out and do it, and you can show that the products of this and this line Z2 intersects both x4 and z4, so no moments about them. So it does not intersect y4, so there will be a moment which you can compute as fc2 plus g c23. Just do the plane geometry. Let's come down to theta 5. So for this we just go back here. So this screw, it's along the z4 axis, so you get 0, 0, 1, and it's at a distance h away, which is this distance h. So you get this expression, and finally theta 6, this is rotated by c5 s5 and 0, 0 h times s5. So this is plane geometry. You can figure it out. So this is just magnificent. I don't have to do DH parameters, right? And what I have there is the real link parameters, which is, this is G, this is F, and then there is H, which is down there. So essentially the three major link parameters, the link lengths, which you can physically measure, they are there, and the angles are there, and I can measure it. And these thetas are the joint positions. So if you take the derivatives, I am in business. The only catch is, to be able to write the whole thing down in such compact form, you cannot write it about the base frame usually. You have to sit in either the third or the fourth frame, depending on which one is more convenient. The fourth one is usually quite convenient. Sometimes the third one. Okay, but you can start from the fourth, and then you can write the whole thing down by inspection. Okay. So once you have done it, we'll just look at this. Yeah.
So such a compact representation depends on the fact that you could find three links in a plane if that had not been so.
So that had not been so?
So the representation would have been more complex.
Yes, perhaps.
So,
but
this is a special case.
Not special case. You can do it for other manipulators also, for KUKAs, and almost every robot will have that. Nobody wants to complicate the forward and inverse kinematics beyond limits. The whole idea is that you should have 6 degrees of freedom in the end, and the computation should be simple. This gives you good things to design robots. You say, I want Jacobian to be simple. I want the forward kinematics to be simple. I want inverse kinematics to be simple. So, so this gives you something. Okay. Clear? So if you are designing a robot, you want this. You said, this is how do you design a robot? 6 axes, how do you stick them? Do you stick them at arbitrary angles? Saying, oh, I don't know, I can always do the forward kinematics. Not a good idea. So, it looks very nice, right? And so then we will see the determinant of the Jacobian is this very simple term. Okay. So we'll come back to this in tomorrow's lecture. And why is that? Because you have this wonderful terms like this column, right? So this column means it is 1 into, you remove this whole row and this whole column. Okay. So we'll come back to this in the next lecture. I want to do this slowly because it's, so what are the things we now have to, so I have a Jacobian which is sitting on the 4th coordinate system, right? I can invert in the 4th coordinate system I can do all kinds of things. So I can find joint rates in the fourth coordinate system. But to really use this, I must then bring everything which I have, all my targets. See, when I was doing the welding problem, all my targets were in a base coordinate system, and I wanted velocities at the tip here, right? So if I can reduce, so I need to bring this velocities at the tip here, define it in the fourth coordinate system, right? Then I am in business. So that we already know how to do. Okay, so we'll look at these issues in the next class in detail. So what I'll do is today I will upload this set after I have fixed these small errors which are there. So try and have a look at it before you come into class tomorrow. So I'll think I'll upload it by about 3 o'clock today. So try and have a look at it before you come to the class, especially these small computation, check out. I would like to know if there are any errors, okay, so that I can correct it. Okay, and then we will push from here. Okay, all right.